So the parts of a wave we can see right here. We've got the crest, the trough, the amplitude only goes from the midline, and the wavelength to the edge. So on this one, the wavelength is from crest to crest, it's 33 centimeters. And the amplitude is from the middle to the top, it's about 10 centimeters. So that's the kind of thing that we're looking for there. So what's the difference between the way that the dots move and the direction the wave is traveling? So we've got our wave on a string situation, right? If we watch this one green dot, we can see that it's only going up and down, whereas the wave, restart this, the wave is clearly going from left to right. So the difference is that oscillation of the particles, the medium, is up and down, whereas the wave is traveling left to right. So if the frequency of the wave is 5 hertz, what is the velocity? Well, it doesn't seem like enough information, but you just said the wavelength of 33 centimeters. So let's go ahead and say 0.33 meters, right? And what's our equation here? We always got to check our equation page. So our equation says velocity of a wave equals frequency times wavelength. So I'm going to plug that in. And then I'm just going to say, okay, velocity equals frequency of 5, wavelength of 0.33, and you get your answer. It's really just that easy. But once you find the equation, that's the hard part, is finding the equation itself. So we get 1.65 meters per second, because I changed this to meters. Now if you kept this as 33, you would get 165, and your units would just need to be centimeters per second. Same idea though. So how can we change the velocity of that wave? This is our conceptual idea, by changing the medium, right? And if there was no medium, like space or the inside of an insulated water bottle, then the wave speed is 0. Alright, so if a different wave traveled 10 meters every 3 seconds and there were 4 waves every second, what would the wavelength of the wave be? So the hint says solve for velocity and frequency, then you can find wavelength. So what's the velocity? Well, it travels 10 meters in 3 seconds. That means 10 meters per, and let me do this as an equation, it means 10 meters per 3 seconds. And I'm not sure why that didn't go into the equation like that. And this is really the same as 3.33 meters per second, right? So that's the velocity. And then 4 waves every second, what does that mean? What is the definition? Frequency means number of waves per second. So that 4 must be the frequency. So what's the wavelength of the wave? Well, okay, let's look at our equations. Now, I didn't give you the rearrangement of this, but this equation still works, right? It's velocity equals wavelength, which I have to insert as a symbol. It's a little awkward. But anyway, once we plug these equations in, we're going to be able to solve for that wavelength. Really, as I said before, setting up the equation is definitely the hard part. It gets pretty easy after you've got the equation. You just have to bring it together and finish it off. All right, so here's all of our Greek letters, and the wavelength one is right here. Wavelength times frequency, and that means we can plug in velocity of 3.33 equals wavelength is what we're looking for times 4. And how are we going to get this? Of course, we will divide both sides by the 4, right? Divided by 4, divided by 4. Remember to work ahead of me. So wavelength equals 0.8325 meters. Alright, so this one asks you to kind of do the same thing without the hint. Travels 8 meters every 2 seconds, so 8 meters per 2 is 4 meters per second. And there are 3 waves every second. So again, we put into our equation, V equals velocity, wavelength times frequency. We have a velocity of 4 equals some wavelength times a frequency of 3. And we get a wavelength equal to 4/3, or 1.333. Now I went really fast there. Rewind and watch it again if you need to. That's the point of these videos, is that you're able to rewind and watch that. Alright, so last two. We've got hearing, how hearing works, and we've got how tuning a guitar string works. So these are two different things that we've talked about before. So let's start with hearing, with all these words. We've done this a few times. The vibrations of Mr. Barentine's throat vibrate the air to create a sound wave. Sound wave vibrates the eardrum, which vibrates the ossicles, which vibrates the cochlea. And then the little hairs inside the cochlea vibrate at different resonant frequencies to send nerve signals to your brain on what you've heard. Repeat that again. Like, watch the video again, I mean, if that didn't make sense to you. And you can pause it on this picture as well. This really goes through all the areas. And then tuning a guitar string, we're changing, what are we changing? We're changing the medium by changing tension. And that affects the wave speed and wave length. The goal is to get a standing wave in the guitar string. Which is when the wavelengths fit perfectly in the medium. The natural frequency of a guitar string matches the resonant frequency when it's in tune. So see how I've used all the words just that quickly. The goal is to get a standing wave in the guitar string, which then the wavelength fits perfectly in the medium. So here's a picture of how like a guitar string does different standing waves. Like the frets are designed. So once it's tuned, if you push down right here, you're going to get a different wavelength of wave fitting in there. And that means a different frequency. And so you'll be able to get what you want. Thanks for watching the review video. Watch it again. Do what you need to do. I will see you next week for the test.